Welcome everyone. Can you hear me well? Probably better with once. Now? Okay, sorry. Hi. Welcome everyone. We are super excited to be here. I think, it's like first in-person PromCon after COVID lockdown, so it's super amazing. And to see, all those familiar faces and new faces in the community. Today we would like to discuss, like a new open source initiative that we are kind of doing in Prometheus ecosystem. So our new open source experimental PromQL engine. What's funny is that I don't think we thought that we'll be working on this 2 months ago. So it's a very fresh idea, but we are working on it, and we are super excited about the initial results. So this is why we are here. We would love to share with you, a couple of details. First of all, why we even developing this, what's the design, how you can contribute, and generally we'll try to finish with some live demo if time will allow. Before short introduction, I have Filip with me today. No, we don't have Filip. Now we have Filip.
Yes. Hi, everyone. My name is Filip. I'm based here in Munich, actually, so it's a bit strange not to travel for a conference, but it is what it is. I currently work as a production engineer at Shopify. I'm a Thanos team member, and I also help maintain the Prometheus operator and Computate metrics.
Thanks. My name is Bartłomiej Płotka. You can call me Bartek. I work at Red Hat. I maintain a couple of things, including Prometheus, Thanos, and lots of Golang projects. I am active in the CNCF, and I recently wrote a book. It's going to be printed like literally this week, so it's done. It's Efficient Go, about Golang and writing efficient Go code, but it's kind of like language agnostic. Lots of chapters are just about optimization, observability, and so on. So yeah, if you're interested, link is there. But we are here to talk about PromQL. So I'm kind of grateful that we are in a PromCon where I don't need to introduce this, but generally this is a Prometheus query language, and it's everywhere, right? It's beautiful, it's powerful, it's flexible. Martin mentioned that some people like it, some people hate it. I don't think I remember anyone hate it, so if you hate it, let me know, but it's generally likable. And many vendors support that, right? And this is kind of the proof of the wide adoption. Every cloud provider, almost all of them, support some kind of like language integration, right? Including Google, Logs.io, Amazon, IBM even. And we also have trainings, right? So we have companies that specialize in training in PromQL. We have amazing cheat sheet from Julius' company, PromLabs. So if you are interested, there is a link as well. So it is everywhere, right? However, versatile language, powerful, grammar is one thing. Second thing is efficient implementation of that language. And the truth is, it wouldn't be adopted if there wouldn't be like an engine, an implementation, a storage that is quick enough to kind of show the powerfulness of this language. So we'll be talking about the implementation part. And fortunately, Prometheus comes with such efficient implementation. We usually call it PromQL engine, right? And the powerful thing about that, it's modular design. What it means that it consumes a string, which is the PromQL query, and it consumes a storage interface and performs computation, right? So it parses the query into the abstract syntax tree, AST. It selects the series from internal TSDB and performs the calculation, processes the samples, and returns the results. So string, maybe scalar, maybe vector, maybe matrix. And the powerful thing is that this is modular in a sense that it lives in Prometheus repo, but it's like a separate package. So anyone can just go to this package, import it, and have a ready engine and provide the storage, and it's that, right? So it's very powerful. So this is what we do in Thanos, right? And this is the same in Cortex, in Mimir. We didn't have to rewrite everything from scratch. And it's amazing because it allows Thanos to be created really, and Cortex, because it allows the ecosystem to innovate and still have some foundations which are very tricky to reproduce. So for example, Thanos, which is like, again, like a project that scales Prometheus and federates Prometheus, we import, PromQL engine directly, just we have a different storage, right? So we essentially have a storage which deduplicate because the data there, now we are talking about distributed systems, so things are replicated, sometimes 3 times, sometimes we are talking to Prometheus in HA, so 2 times. So this deduplication has to be added. And then we have remote storages. And we call them Store API because this is just gRPC API that gives you metrics. It can be anything. It can be Prometheus. We have components, Thanos Receiver. We have component for Store Gateway, which is for object storage kind of data. We have rulers. We have other things. And you can integrate with your own system as well. So it's amazing because we could start very easily. And for a long time, it was good enough solution. However, as with everything, there are challenges. And this is why we are here. We would like to share with you some of those and why it triggered our ideas to improve something. So first of all, technically speaking, those challenges doesn't exist in Prometheus. In fact, it's perfect. And one, like we already have evidences of that in yesterday talks. I think Ryan mentioned about when he was querying and trying to really load test Prometheus, querying didn't even increase memory, right? So things are very, very efficient and designed for Prometheus. However, Prometheus Prometheus is pragmatic, and Prometheus project tries to evaluate the requirements, and we designed Prometheus engine to satisfy those. And the requirements are very, very specific, right? So we have in-memory calculations, so every data is in memory. If it's not in memory, it will be in memory very soon using this memory mapping feature of Linux. And so that's kind of simplify things. Another kind of requirement is that Prometheus is within, it's just a process that actually do many things. So it not only does query computation, but also scraping, also computation, or compaction, also recording rules, alerting rules, and all those things has to work. So you don't want to spend too many CPUs on querying because you will essentially, it will be noisy neighbor for your Go routine that is scraping, which is super, super important. So that's why, the engine has design kind of goal to maintain this isolation and not be noisy neighbor. Another thing is that the data set is like, small to medium. So we are talking about maximum 10 millions of active series, maybe, roughly within a month. Of course, you can make a bigger setup of Prometheus, but this is usually the data set Prometheus engine has to deal with. So the decisions are kind of based on that. We have PromQL engine kind of executes computation series by series, roughly. It's sequential. So by design, it should not use more than 1 CPU. And then everything is in memory. So those are like critical design decisions. Now, when you compare that with any other like distributed system, like Thanos, Mimir, or Cortex, things are a little bit different, right? So we have data scattered around the world, sometimes in multiple regions, in object storage, in memory, in disk, and like it's just more, more kind of like distributed and scattered. Secondly, we have a separate process. We have this Thanos Query component, which is microservice that only do PromQL computation. So there is a room for scheduling this in large clusters and actually use 100 CPUs, not only 1. So why we are limiting here, our scope, our engine. Finally, or like almost finally, there is like a big data set, right? So we are talking about billions of active series and years of data, because we distributed this project for a reason, to be capable of scaling like that. So yeah, we are handling this kind of amount of data because, again, this is what a global system has to deal with. Finally, replication. I already mentioned we have replicated data heavily, so we need to have, engine. Ideally, engine helps with that. But the problem is it doesn't, right? Like as you learned in previous like design goals, the PromQL engine was designed for something else. So there is theory that, and we've seen that kind of on the wild, like at some point, Thanos Query was, booming, very slow, and was the single point of failure because PromQL engine was not kind of designed for that. And you know, what's great is that we had a talk just before from Marco and Susanna, and they talk about exactly the work we did within the community for the last 2 years to mitigate many of those problems, right? So I won't be repeating this, but generally we're talking about another component. We call it query frontend. It actually was designed by, we started in Cortex. We kind of imported that in Thanos. So we have this horizontal query sharding, splitting by day. We have response caching. Recently, we added both Mimir and Thanos vertical query sharding on the different levels. And then we have query pushdown as well on the leaves. So we did a lot of kind of work to make things faster and better. But I want you to see the pattern, right? So we do some magic here. We do some magic here. And here we don't do magic yet, right? Or we use old magic. So we want to challenge that. And I think it was kind of this closed box pattern where we are maybe afraid to touch something that was so perfect, so kind of optimized in the past. So we want to kind of address this elephant in the room, something that we rarely touch. And essentially it was scary because the amount of redesign work and kind of complications and details. But some people are crazy, and we would try to go with you, what if we would redesign it? And in fact, we have a ready solution that works. So I will let Filip to explain that in detail.
Thanks. OK, so before we take a look at how the query engine in Prometheus and what we're doing in Thanos works, we can first try to visualize what a query execution looks like. So we can first visualize, we can take this two-dimensional plane, and we can visualize time series data as on this y-axis and time on the x-axis. And then the samples that we have here, they are basically observations that we either scrape or we remote write. And so when we evaluate a range query, what's going to happen is we're going to select discrete steps in this time in the range, basically. And for each of those steps, we select points that are closest to the timestamp of the step. And for each of those steps, we independently run the PromQL expression. So what the Prometheus query engine gives us back is basically discrete points, so one value for each of the steps. And something like Grafana or the Prometheus UI is going to draw a line to make that line look contiguous. But it's really discrete steps that we're getting back, discrete points that we're getting back. So the way that query evaluation works in Prometheus right now is so Prometheus takes the input query, which is a string, parses that into what we call a syntax tree or an abstract syntax tree. And then it will start evaluating the expression bottom up, so from the leaves going upwards. So it's first going to evaluate the selector, then do the rate, do the sum. It's going to do the right-hand side of the tree as well, and finally it's going to do the division. There are some optimizations. For example, the rate can be now pushed into the selector and stuff like that, but these are very context-specific. They're not generic optimizations. They are hand-coded into the engine. So if we unwrap this execution now, we see what Bartek was talking about before. We see this very sequential-like execution model, which also makes sense because we have a single thread at our disposal. But we also, if you look at the code and if you do some benchmarks, we notice that there's a certain buffering happening between all of these steps. So for example, if you do a sum by, the rate operation is going to buffer all of the results from the beginning of the range to the end of the range, and then pass that into the sum. So this can also lead to memory bloat from time to time, and stuff like that. So the binary operator is going to buffer as well, and things like that. So with this kind of constraints that we have in Prometheus, and understanding how the Prometheus engine works, we've basically started a fully multi-threaded version of the PromQL engine that currently lives under the Thanos Community organization. And we don't want to reinvent the way that we do PromQL, but we want to redesign it so that it's multi-threaded first by design. And also from day one, we have full compatibility with the engine API. So it's a drop-in replacement. If you're using the PromQL engine from Prometheus, you can simply swap it in. And we also have full support for the full PromQL grammar. And we do this by simply falling back to the Prometheus engine in case we don't yet have support for a certain function. So for example, right now we cannot calculate a quantile over time. So if we detect a quantile over time in a PromQL, we'll simply instantiate or use an instance of the Prometheus engine and execute the query that way. So by doing this, we're able to kind of deliver things much in an iterative manner and also experiment with this design and see where it's going. Also, it's worth pointing out that we're not starting fully from scratch. So we've taken a look at what other databases do, how other query engines work. So there's this very influential paper from 1994. If you're interested in the topic of query engines, this is a good place to start. It kind of describes a framework that can be used for building engines in general. And this is what we've used to kind of as a foundation with some modifications for the Thanos engine. OK, so let's now take a deep dive and see what this thing looks like. So the fundamental building block that we have is this concept of an operator. And we see that an operator is an interface, which means that there are different types of operators in the system. And each operator implements a next function. So the next function returns what we call a step vector or a vector. And these vectors are exactly these vertical slices that we saw in the previous slide. And so the way that we execute a query is we chain different types of operators together. And each operator calls next on its downstream operator until the downstream operator has nothing else to return. So in this particular case, the aggregate, which can be a sum or an average, is going to call next on the function, is going to call next on the selector. The selector is going to return the samples for T0. The function, if that's a rate, is going to do the rate on those samples, return that to the aggregate, which is going to maybe, if it's a sum, is going to sum everything together. And at that point, we basically have the result for T0 for that particular query. And then we simply repeat this process until we've basically gone through all steps. So to see why this model is flexible, also worth noting that because each operator implements the same interface, we can combine this operator in any different way. And this combination or this graph is what we call an execution plan. So to take a look at a specific query, again, this summary that we keep using all the time, the way that we would execute this particular query is we would create an operator for the selector. That operator is processing steps from T0 to Tn for this particular kind of sub-expression of PromQL. Then we create a rate operator. And we can immediately see that we have a pipeline-like execution model where as soon as the selector is done with processing T0, it's going to hand it off to rate. And now while rate is processing the step T0, the selector is already capable of processing T1. We can do the same for sum. So basically, while sum is working on T0, rate is working on T1, the selector is working on T2. So now if we run each of these operators in a different Go routine, we've basically parallelized the execution of the entire PromQL expression. So every sub-expression can be run in parallel, with this exception of like the few first steps, which are cold start. But keep in mind that the range query has 1,400 steps, so those first steps are not very significant. And if we make this expression more complicated, turn it into a binary expression, we can do the same thing. We basically kind of pipeline and stack operators this way. If we now run them in 7 Go routines, we basically have full parallelization. So this is how we build parallelism inside an operator, which can also this is how we build parallelism between operators. We can also have parallelism inside an operator. So we've noticed that decoding chunks, so decoding samples from chunks, doing rates, stuff like that, can be quite compute intensive. So we might want to allocate simply more CPU cores or more threads to those operations. So in this particular model, we would simply instantiate multiple instances of the rate and of the selector. And because we have a consistent interface, we can kind of interject a synthetic coalesce operator is going to merge those streams and hand the result to sum. So now we have 3 parallel rates and 1 parallel sum, so we can basically run this query in 4 Go routines. Okay, so speeding up, so using multi-threading is just one way to speed things up. We can also make queries simply more optimal for execution. So we don't necessarily have to execute queries as they come in from the user. And the way that we do this, and that we've kind of seen before in the previous slides, is that we've decoupled the syntax tree from the execution model. And so now this kind of syntax tree that we parse, we call that a logical plan. You can think of it as a logical plan or a declarative plan of what needs to be done. And so we can run multiple independent optimizers on that plan, and we only execute the optimized version. So what we have, for example, in the current implementation is if we have this particular binary expression, we see that on the left-hand side and on the right-hand side, we are selecting the same metric. So in something like Thanos or Mimir, this would cause basically 2 network calls, and it would also cause the engine to hold 2 copies of the same time series, because the right metric, so the right series, the right selector is a superset of the left one. So using an optimizer, we transform this expression into something like this. So we merge the 2 selectors into one, and then we inject, again, this synthetic operator on the left-hand side for basically, we have to do it for correctness, that's going to filter the data set in memory. So basically, we reduce memory usage because we now have only 1 copy of the data, and we also reduce latency because we don't have to do network calls. And also in the future, we are looking into adding some sort of physical optimizers. This is still up in the air. And also Marco spoke a bit about this, how they are planning to do it in Mimir. But essentially, we want to have fine-grained control of how much concurrency we want to assign to a given query. So we might want to do that based on certain statistics that we pull from storage, or based on how many other queries are currently running in the engine. So if we have a lot of queries running at the moment, maybe we want to tune that down and reduce concurrency. OK, so let's look at some benchmarks. So we kind of run a suite of benchmarks on a very regular basis. And we run that both on in a single core environment by simply setting go max prox to 1, and with basically all cores that we have on the machine. And what we see is what's interesting is that even for the single core setup, we have actually pretty good performance. We can run things faster than the Prometheus engine. Something like a sum by, for example, would run 70% faster. So we have to obviously do additional benchmarks to see if there are any cases that we're missing that might cause regressions based on how the data looks like. But so far, things are looking quite good. And on the multi-core setup, basically, we see that that gap is even wider. And I personally think, this is just my opinion, I personally think that we can even make the gap bigger, because the execution plan that we generate right now is definitely not optimal. So there's a lot of room for improvement there. We also keep track of memory. So right now, it's
Oh yeah, let's do this. Let's mirror screen.
Mirror the nodes.
And because I need to mirror it anyway for demo, if this is going to happen. But it's not helping. Two good results. Nope, binding. Too good to be true.
Okay. Yeah, so we keep track of memory as well. We benchmark memory usage. Right now, we're kind of satisfied where we are, with the exception of this history and quantile function that we added a week ago, and there seems to be opportunity for improvement there. But other than that, things are looking quite okay. Also worth keeping in mind that if we're going to run things on multiple cores, it's hard to avoid using more memory because each of these independent operators, shards, whatever they are going to have their own memory buffers that they use. So this is simply a trade-off that we have to accept. All right, so to summarize, we basically have a hidden flag in Thanos. It's not even experimental. It's not documented that you can use to toggle this engine. We haven't documented it because it's such a new project. But we at Shopify, for example, have a small setup on the side that we use a Thanos query with this engine enabled, and we kind of poke around it and use it, and so far it seems to be fairly correct. And also, as I said, we have this fallback mechanism, so if we don't have support for a given function, we'll fall back to the Prometheus engine. Right now, this is what the support matrix looks like. We used to have history and quantile until yesterday when we saw history in the making. But the new native histograms that have just been released will work on adding that support there as well. And yeah, that's it. Also, I would like to say that we would not have been able to come this far without different contributors from different companies. So if you're obviously interested in this topic, interested in contributing, or even just opening issue, feel free to do that. All right. So now I hope we have time for a very quick demo.
Okay. Yeah, let's do it. So actually, I want to show you the demo setup first. So roughly, the setup is like this. We have, a Thanos setup, very simple one. We have two store gateways, which simulate maybe you have two object storages, and then we have two Thanos queryers that points to the same storage, to the same store gateways, and they don't know about each other. And one is using a PromQL engine, like the standard one, and second has this flag enabled. So we have a PromQL enabled, and this is like literally, Thanos master, Thanos main branch. And I wanted to simulate like very large kind of setup, so I have those chunky blocks from, I don't know if I can tell that, but it's production. But it's like very analytic-based tenant, so they're super, there's high churn. They are like 2-week block. 8 million series. I have 4 of them, so together it's like 25 million of active series for 2 weeks. And I will perform a query against data. I will essentially query a cluster version metric, which will roughly touch, over 120,000 series, 40 million samples, and a lot of chunks. So generally, I just want you to understand that I made it, big to kind of have like a nice load test. And it's running only on my laptop, right? So let's go. I have this nice end-to-end framework that we created with Cortex team. I think Marco started that. We use that today as well. So I have my containers essentially, defined in Golang, and it's just easy to maintain. So we see things starting up. I have Prometheus just to monitor my setup, my testing setup. Let's wait for Parka, which is continuous profiling I have already in. I have tracing, of course, because how would I else debug things? And then I have 2 query UIs. So we see 2 Thanos UIs. I think I can actually make it bigger, yeah. So let's do it. So first I have old PromQL, standard PromQL. It's not old, we still use it. So let's perform this query on a standard PromQL. So essentially we are performing a count over those 120 series, which is also like duplicated. So we can see it's fairly fast. It's 5 seconds now, and we can see load time here, 5 seconds. And it only produces 1 series because it's a count. But let's see what it how fast is on the enabled query. So we already say it's faster, like almost 2. Depends on the setup. It's it's not very like scientific benchmark. You know, I'm running 1,000 things, including HDMI kind of whatever. So, you know, but you already see improvement. What's amazing, we can actually try to explain why it's so fast. So we added this kind of explanation pattern because in normal MySQL you can do that. So why not, since we are adding query planner, those phases, why not just show what's happening? So we see that it's kind of like physical plan we execute. You see that there is some aggregation going on, which is count. We have some concurrency between. This is this pipeline that Filip mentioned. We have coalesced because we want to essentially shard. My computer has 12 logical cores, so we thought that, you know, this execution plan said, okay, you have 12 logical cores, let's do shard by 6. So you can see we essentially fetched actually within one core, but then we have this selection, and then inside the engine kind of split into six shards, right? And this is already why it's faster on top of other things. Okay, let's make it more complicated. So we have this special query that Filip mentioned, which is when you select the same metric on binary operator. No, don't worry, just turn off and on, and yeah, I just perform it. I think. I hopefully click the button. No, yes. Let's try again, but luckily it was the end of the demo anyway. Okay, let's go quickly. Yeah, I will. One attempt, but anyway, what is performing, hopefully, is this double query with like essentially we are selecting the same metric, right? But we are doing this in a normal standard query. You have this this query essentially selecting data twice from the machine. So we have 10 seconds on old. Let's see new one. Yeah, let's perform. Things are changing, so let's see. Okay, it's 3 seconds versus 10 seconds. So it's already a huge improvement. The data is exactly the same. If we explain, hopefully I will manage to do it. So we have a physical plan with before optimizations. You can see some sharding and some essentially selection here for one binary part of binary operation, and then second binary operation there is selection on other side, selecting the same metric just with additional filter at the first part. But you know, our engine noticed that, it sorted the matters, it replaced cluster version with this filter optimization. So what we will see here in the optimized version is that we have a series selector that only fetches everything, but this is a kind of like tricky, but this is a memory address of this component in code, and you can see the memory address are the same for shards, is the same across binary operators as well, which proves we use the cached version, and then we just filter on top. We filter virtually in the engine instead of a storage, asking storage for a separate data set. And this is very visible in Jaeger UI as well, because we can kind of see what's happening. So let's take this 9 seconds. I hope this is the same query, yeah. So this is old 9-second query apparently, and let's do yeah, many things happening, but what I want to show is essentially one select and then second select. You see 2 selection from storage happened. They were, you know, overall concurrent, but still you use, you know, double amount of memory, and there is some kind of work to be done on computation level to fan out, to deduplicate all of those. So it's non-trivial effort. And then this is the fast query, the new PromQL. Thanks to the optimizer, we have only one select, right? Because it merged, and it's actually very faster. And the reason is that because I'm doing all my single machine, so all those surrogators, they are noise neighbors to each other, I guess, and it's slower. So this is the power of new PromQL engine, and we just started, right? So we already have planned for like a lots of amount of different optimizations that actually there are on Prometheus issues, some of them, some ideas to optimize further. So we will be only going further. And our idea for this effort is to really really make sure to have community also enabled to contribute those optimizations. So all those operator kind of pattern, the optimizers, are really about to create a framework that is easy to add different optimizers for your specific environment, right? So we are enabling the gate, hopefully, of like very, very cool optimizations that will make our systems cheaper and faster, right? So that's it from us. Thank you, and we are welcome. Yeah, any questions if you have any.
Is this one? Yeah. Okay. Thank you very much. We're over time, so could maybe do one if it's a really good question.
Only good questions. Yeah. We'll filter them.
No, nobody's brave enough to claim that. All right. Well, we'll go to a break now and back at 15:15.